Our next problem is linear harmonic oscillator. Okay, so let us start with the expression for the potential energy of harmonic oscillator. The expression for potential energy is we know it's a one-dimensional harmonic oscillator, so half k x square, where k is force constant. Okay, now k we can express in terms of mass and angular frequency m omega square. So the potential I can write as half m omega square x square, right? So now we want to solve this. So it's a quantum mechanical oscillator or quantum oscillator. So an example is a vibrating diatomic molecule or a vibrating atom in a solid lattice. Okay, so we want to solve the we want to obtain the energy of this harmonic oscillator by solving the Schrodinger equation. Okay, now we note that this potential energy is time independent. So okay, so we don't have to solve the time dependent Schrodinger equation. The wave function is separable. You can separate spatial part and time dependent part, and we know the expression for time dependent part, e raised to minus I e t by h cross. The space dependent part satisfies time independent Schrodinger equation. So we need to solve the time independent Schrodinger equation to obtain the space dependent part of the wave function. Okay. So what is the time independent Schrodinger equation? So I am using this form minus h cross square by 2m. Instead of partial derivatives, we can use full derivative. Because our wave function depends only on x now. It's a one-dimensional oscillator. Plus, so minus h cross square by 2m d square psi by dx square plus v psi. Now v is this, potential energy is this, half m omega square x square psi is equal to e psi of x. So this is our equation 1. Okay. Schrodinger, time independent Schrodinger equation. So first what we want to do is to convert Schrodinger equation into dimensionless variables. Okay, now it is a differential equation, a partial differential, not a partial differential equation, but an ordinary differential equation, because we are differentiating only with respect to x. So now it's an ordinary differential equation only in x, in terms of the position coordinate x, and you have this variable. So there is one variable is x and another variable is the energy. Okay, now I want to express so in order to solve a differential equation, sometimes the solution of this differential equation is somewhat lengthy, and we will not completely solve this equation. We will not go through all the steps, they are very lengthy. You will study the complete solution in your MSc class. Okay, we can do it here also, but it takes some time. Okay, so when we have a differential equation and we want to solve it, often the first step is to express this differential equation in terms of dimensionless variables. So that's what we are going to do now. Let us see how this can be done. So let me introduce two dimensionless variables. Instead of x, I am introducing theta. Okay, let theta is equal to beta times x. Okay, where beta has the dimension of x inverse position. So if beta has the dimension of x inverse, x has the dimension of position. Okay, so when I say x inverse, I mean position inverse. Okay, length raised to minus 1. So this is inverse position and this is position which has dimensional position. So beta into x is dimensionless. Okay. What is the form of beta that we will see, and alpha is equal to E by E0. What is E? It's a total energy of the harmonic oscillator. Okay, we know that E is here it is. E is the energy of the harmonic oscillator. Now I have introduced a new variable E0. Okay, and so the variable E0, where E0 has the dimension of energy. Okay, so E is energy. Look at this term. E is energy. E0 also has the dimension energy. So E by E0, that is alpha, is dimensionless. So what we are going to do now is we have introduced two dimensionless quantities, theta and alpha. So we want to rewrite this equation 1, Schrodinger equation, in terms of these dimensionless variables. Okay, so I want to rewrite this d square psi by dx square into, this is differentiation, second order differentiation in terms of x. So I want to rewrite this second order derivative into d square psi by d theta square. Okay, so let us see how this can be done. So this is it. X is a function of theta. Okay, this implies d by dx of psi of theta. Okay, the point is this. In here we have d psi by dx and d square psi by dx square is there, but psi is a function of x. Now I want to, since x is a function of theta, see here theta is equal to beta times x. So x is a function of theta now. Okay, that means psi, the wave function psi, is also a function of theta. So I want to re-express this wave function and its derivative, second derivative, in terms of, completely in terms of theta. Okay, so if x is a function of theta here, if x is a function of theta, it implies psi is also a function of theta. Then how do we evaluate this quantity d by dx of psi theta? Okay, so d by dx of d by dx of psi theta is equal to d by d theta of psi theta into d theta by dx. We are using function of a function rule. So what is d theta by dx? Look at this expression. Theta is equal to beta times x. Okay, so d theta by dx is nothing but beta, right? So we have beta times d by d theta of psi theta. Let's go to the second derivative. So next, d square by dx square of psi theta is equal to, so this is we have to take d by d theta of d psi by dx. But what is d psi by dx? So look at the previous line. D psi by dx is nothing but beta times d psi by d theta. Okay, so d by d theta of d psi by dx into d theta by dx. Okay, we are d square psi by dx square means d by dx of d psi by d theta. D by dx of d psi by dx, right? D psi by dx is this one, beta d psi by d theta. Okay, so taking one more differential, what I have done is I repeat this line. Okay, d by d theta of this quantity, this which quantity, d psi by dx, that is beta d psi by d theta into d theta by dx. Okay, I hope this is clear. We are just repeating the previous term. Now what is d theta by dx? Beta. And you have another beta inside the square bracket. So we have beta square d by d theta of d psi by d theta is d square psi by d theta square, where psi is a function of theta. Okay. So now we can substitute for the second derivative in the Schrodinger equation. D square psi by dx square we have expressed as beta square times d square psi by d theta square. Okay. And other terms also, here in terms of x square I can rewrite in terms of theta, it is theta by beta, right, whole square. And in terms of e I will write here, from here, alpha times e0. Okay, so let us see that. So our Schrodinger equation 1 becomes, so let's rewrite equation 1. Equation 1 becomes minus h cross square by 2m then d square psi by dx square. And now to look at the previous line, d square psi by dx square is beta square times d square by d theta square of psi theta. So it's now a function of theta, sorry, theta. Okay, not equal to, there is one more term, potential energy term. So plus half m omega square x square, instead of x square I can write theta square by beta square. Theta equal to beta x, so x is theta by beta. Okay, theta square by beta square. So this is the left hand side, equals alpha, instead of e let me write alpha times e0 psi theta. Right side e psi becomes this. Okay, so this is not completely dimensionless, because in this expression you have beta which has some dimension, and you have e0 which also has some dimension, right? Okay, so what I am going to do is now let us make the coefficient of the highest derivative as 1. Highest derivative is d square psi by d theta square. So let us divide throughout with the coefficient of this highest derivative, okay, which is minus h cross square by 2m beta square. Let us divide throughout with that term. So what you get, the first term becomes d square by d theta square psi theta. Then there is a minus sign because you are dividing with minus h cross square by 2m beta square. So minus. The second coefficient becomes, let me use a square bracket here. Let us say you are differentiating, dividing with minus h cross square by 2m beta square. So you are basically multiplying with 2m by h cross square into 1 by beta square, right? So 2 will cancel. Here you have m square omega square by h cross square. Then there is a beta square already in the denominator. There is one more beta square, so you will have beta raised to 4. Let me close this bracket here. Then you have theta square psi theta. Check whether this is correct. Okay. Equals, on the right side again you have a minus sign. You have to put a minus sign because the coefficient of the highest derivative is negative. Let me put a square bracket again. So you are multiplying with the reciprocal of that. That is multiplying with, you are dividing with minus h cross square by 2m beta square. That means you are multiplying with 2m by h cross square into 1 by beta square. So this term will be 2m e0 by h cross square 1 by beta square. Let us close the bracket. There is one more alpha here, alpha psi theta. Okay, this completes it. So why we have put something in the square bracket? Okay, let us see. What I have done is, now look at this term, d square by d theta square psi theta. Remember that theta is dimensionless. So this second derivative is now perfectly dimensionless. Psi is a function of dimensionless variable theta, and differentiation also is with respect to theta. It's perfectly dimensionless. Now in the second term, I have put some quantities in the square bracket, right? And what is outside the square bracket? Theta square psi theta. Remember, theta square is dimensionless. Theta is dimensionless, and psi is a function of theta now, so it's also dimensionless. Okay, so I have put the dimensionless quantities together, and other quantities I have just put in the square bracket. Right side also, this alpha is dimensionless, psi theta is dimensionless now. Other quantities I grouped together. Okay, so let us look at these terms in the square bracket. There is a square bracket here, there is a square bracket here, okay, here. Now suppose the terms in the square bracket, okay, consider this one. Suppose this entire term is equal to 1. Okay, if this is equal to 1, then the remaining terms in this here, theta square psi theta, is perfectly dimensionless. Similarly, if this entire term is equal to 1, okay, then the other remaining terms here is alpha times n psi theta. Alpha is dimensionless, psi theta is also dimensionless. So what we want to do now is put the terms in the square bracket equal to simply 1, so that the entire equation is now dimensionless. So if this is equal to 1, what will be the value of beta? Okay, so if this is equal to 1, we can say, so let us say m square omega square by h cross square 1 by beta raised to 4 is equal to 1. That means if you take beta, so far we have not defined what is beta. Okay, I have just said that beta has the dimension of x raised to minus 1, but I have not defined it. Let us define it now. Now if you take beta raised to 4 to the right side, beta raised to 4 is equal to m square omega square by h cross square. Take the square root. So beta square equal to m omega by, look at here. So beta square will be equal to m omega by h cross. So what is beta? So from here, beta is equal to square root of m omega by h cross. This is beta. Okay. Now I will, earlier I said that beta has the dimension of x raised to minus 1. Let me give a short homework here. You from this expression, beta is equal to square root of m omega by h cross, you verify whether beta has the dimension of x raised to minus 1 or position raised to minus 1. Okay, you can do something to this equation and you can easily verify that. Okay, so I just claimed that beta has the dimension of x raised to minus 1. From this expression you will get that. So now we have defined what beta is. Let's go to this second term, this term on the right side, the square bracket on the right side. Put that equal to 1. And from that, now already we know what is beta, so we can substitute for beta square here. And there is the unknown quantity E0. We want to find out the value of E0. Earlier we just said that alpha is equal to E by E0. We said that E0 has the dimension of energy. Okay, but let us define it now. So let us go here and 2m by h cross square E0 1 by beta square is equal to 1. Okay, so what is E0? E0 is h cross square by 2m into beta square. But now we know what is the value of beta square, so h cross square by 2m. Okay, look at here, already we have obtained what is beta, square root of m omega by h cross, that is beta. So what is beta square? M omega by h cross. Okay, so let us come here. Beta square is m omega by h cross. So that's equal to 1 h cross will cancel, mass will cancel. Okay, m is the mass of the harmonic oscillator. Okay, oscillating particle. So what you get is half h cross omega. that is E0. Okay, so this we have defined. From this it is directly clear that E0 has the dimension of energy, right? You have h cross omega here. We know that h cross omega has the dimension of energy. So E0 has the dimension of energy. It's easily verifiable. This is not exactly directly visible here. How beta has the dimension of x raised to minus 1, that part you have to um, check. Now let's remember a few points here. This 1 by beta is called 1 by beta. So 1 by beta should have the dimension of length. Okay, is called characteristic length. Characteristic length of linear harmonic oscillator. Okay, or beta inverse. And this quantity here E0. Okay, E0 has the dimension of energy. E0 is called E0 is called characteristic energy of linear harmonic oscillator. Okay, so that's it. 1 by beta is called characteristic length, and E0 is called characteristic energy. Okay, so this is characteristic energy, and 1 by beta is characteristic length. Okay. And one more point about characteristic energy. Later we will see that the ground state energy of linear harmonic oscillator is half h cross omega. Okay, this is always true for bound systems. Characteristic energy will always be equal to ground state energy. Okay, this is not only for linear harmonic oscillator, for other bound system also we can show this. So what we have done here is we have rewritten Schrodinger equation in terms of, or using characteristic length and characteristic energy. Okay, we have rewritten Schrodinger equation in terms of the dimensionless variables. So what is the Schrodinger equation now? See here, d square psi by d theta square. This entire term in the square bracket on the left hand side is now 1. Now we have remaining term minus theta square psi theta, right? Minus theta square psi theta. On the right hand side again, the term in the square bracket is 1. Okay, that's the way we have chosen beta and E0. Okay, and what is the remaining term? Minus alpha psi theta. So let us take this minus alpha psi theta to the left side, and then our Schrodinger equation becomes, what is it? D square by d theta square psi theta plus, so we have taken this minus alpha psi theta to the left, so it becomes plus alpha psi theta. Then there is a minus theta square here, so alpha minus theta square psi theta equal to 0. This is equation 2. This is again Schrodinger equation. Okay, we have expressed the Schrodinger equation in dimensionless variables. Okay. Okay, now this is only the starting point of the process of solving Schrodinger equation. The first way is, not only for Schrodinger equation, when we get a differential equation, sometimes often one of the techniques, the starting techniques is to rewrite the differential equation into dimensionless variables. So that we have done now. But again, there are many steps involved for the solution. Okay, we will not go into all these steps. So let us directly go to the solution now. Okay, so let us in order to solve this equation at one stage, okay, we have to apply the boundary condition. So what is the boundary condition here? Remember that boundary conditions are often or nothing but admissibility conditions on the wave functions expressed on certain on the boundaries. Here the boundary condition is simply this. um, the wave function psi theta should go to 0 as theta goes to plus or minus infinity. Okay, as theta goes to very large, now wave function is expressed in terms of theta, the dimensionless variable. So as theta goes to plus or minus infinity, wave function should go to 0. That's it. So at the two boundaries, plus infinity and minus infinity, the wave function should go to 0. You remember that this condition is simply the condition that the wave function is normalizable. There is one admissibility condition that our wave function should be normalizable, and mathematically the wave function is normalizable only if it behaves like this. When the independent variable goes to plus or minus infinity, the wave function should go to 0. Okay, so if when we apply this boundary condition, okay, then we can show that. How we can show that is it's a lengthy procedure. So let's just take this alpha equal to 2n plus 1. Okay, this dimensionless variable alpha that we have introduced, it becomes quantized when we apply the boundary conditions, where n is equal to 0, 1, 2, etc. N is an integer or quantum number if we use that term. So the consequence of applying the boundary condition is that alpha is now quantized. But what is alpha? Alpha is E by E0. So E by E0, remember alpha we have introduced as E by E0. That's equal to 2n plus 1. So E is equal to 2n plus 1 E0. You can see that if alpha is quantized, then energy is also quantized. So we can put a suffix here, En is equal to 2n plus 1 E0. But what is this E0? 2n plus 1. We have obtained E0 here. This is characteristic energy. Okay, see, E0 is half h cross omega. Okay, so we can substitute that. So E0 is half h cross omega. Often it is written like this, a 2 we can take outside, so 2 will cancel with half here, so this becomes, when you take 2 outside, 2n becomes n, and here you have to put a half, so n plus half h cross omega. These are the energy eigenvalues of harmonic oscillator, where n is 0, 1, 2, 3, etc. These are the energy eigenvalues of harmonic oscillator. Eigenvalues of Hamiltonian. Remember that time independent Schrodinger equation is an eigenvalue equation of Hamiltonian operator. So these are the eigenvalues of Hamiltonian operator. That's why we call it energy eigenvalues. So energy eigenvalues of harmonic oscillator are n plus half h cross omega. Okay, so what are the, let's write down the properties here. Okay, so what are the properties of these energy eigenvalues? Maybe I will write it here. Properties of energy eigenvalues. Properties of En. Okay, one, we can see that En values are quantized. En are quantized. That is obvious. We have only some specific values for specific values of energy. N equal to 0, 1, 2, 3, etc. Right? Now E minimum is equal to, it is E0, right? What is the value? Look at here, when you put n starts with 0 here. Okay, n is equal to 0, 1, 2, 3, etc. So when you put n equal to 0, what you get is half h cross omega. So this is half h cross omega. This is the ground state energy of harmonic oscillator. And this is often called a 0-point energy. The reason is that an example of a harmonic oscillator is quantum harmonic oscillator is a vibrating atom in a solid or a vibrating diatomic molecule. Now suppose you decrease the temperature, then the vibrational energy will decrease, the amplitude will decrease. But even if you go to zero temperature, even if even when you approach zero temperature, the energy of the quantum harmonic oscillator will not go to zero. It becomes some finite, it remains at some finite value, half h cross omega. So the energy at even at zero temperature, in that sense it's called 0 point energy. So it's half h cross omega. Now we note that earlier I said that this characteristic energy, okay, the expression is half h cross omega, and I mentioned that characteristic energy of any bound system will be always equal to its ground state energy. So here in the case of linear harmonic oscillator, we can see that ground state energy is half h cross omega, okay, which is same as characteristic energy. And another point we want to note is that E minimum, ground state energy, is not non-zero, right? So this is the point. E minimum is non-zero. Now this is true for any bound system. In fact, these two properties are common for any bound system. Energy values are quantized for a bound system, and minimum energy is non-zero. And this non-zero nature of minimum energy is a consequence of uncertainty principle. We have discussed this when we considered particle and infinite potential. Well, there also minimum energy is non-zero. So because using uncertainty principle, we can argue this when delta, considering a one-dimensional case, as in this one, delta x is finite here in the case of a linear harmonic oscillator, or in the case of a particle in an infinite potential well or finite potential well. So if delta x is finite, we can show that delta p is always finite according to uncertainty principle, uncertainty relationship. So minimum energy cannot be zero, because if minimum energy is zero, then minimum momentum is zero. Then for that state, for the ground state, you can clearly say that since the momentum is zero, delta p is zero. But if delta p is zero, then delta x should be infinitely large. But for a bound system, delta x is finite. So according to uncertainty relationship, if delta x is finite, delta p should be finite. This implies that minimum energy has to be non-zero, should be non-zero. So it's a consequence of uncertainty relationship. Now the third property for the energy. So the first two properties are specific to these are general to any ground state system. But the third property is specific to linear harmonic oscillator. The third property is the energy difference, delta E. Energy difference between the nth state and n plus 1th state. That means the energy difference between two nearby states. Okay, what is that energy value? It is always h cross omega. Okay, so energy difference between adjacent energy levels in a linear harmonic oscillator is always h cross omega. You can see that from here. N0 is half h cross omega. What is N1? 3 by 2 h cross omega. Difference 3 by 2 h cross omega minus half h cross omega. It says h cross omega. N2 is 5 by 2 h cross omega. So N2 minus N1, 5 by 2 minus 3 by 2, h cross omega. So adjacent levels are always spaced by h cross omega. In other words, energy levels are equally spaced. If we want to plot energy levels of harmonic oscillator, okay, let me plot here. Energy levels of harmonic oscillator will look like this. By convention, we plot energy levels within the plot of potential energy function. So this is the shape of the potential energy function, parabolic for harmonic oscillator. Okay. Okay, this point is x equal to 0. Okay, this is a potential energy function. So energy levels will look like this. This is ground state energy, n equal to 0, E0 is half h cross omega. Okay, n equal to 1, E1, n plus half h cross omega, right? So 1 plus half, that is 3 by 2 h cross omega. Then n equal to 2, E2, 2 plus half h cross omega, that is 5 by 2 h cross omega. So we have drawn first 4 energy levels. Okay, 7 by 2 h cross omega. So the adjacent levels are always spaced equally. The energy levels are equally spaced. In the textbook in Arthur Baser, you can see a comparison between energy levels of hydrogen atom. You have studied this in Bohr atom model. Energy levels of particle in an infinite potential well or particle in a box, one-dimensional box, and energy levels of a linear harmonic oscillator. Okay, it's very instructive for comparison. The spacing between energy levels is a characteristic property of that particular system. Remember that in particle and infinite potential well, the spacing was increasing. The spacing between adjacent levels was, I think, 2n plus 1 times E1, where E1 is the ground state energy. So it was increasing like E1, 3 E1, 5 E1, 7 E1, etc. So here it is equally spaced. In the case of hydrogen atom, you try to plot it and see what happens. Now let us go over to the wave functions or Eigen functions. Okay, let us consider here. So again, I am not going to the detailed solutions. I will just write down the wave function here. So the solution of Schrodinger equation will be like this: psi and theta in terms of dimensionless variables. Okay, its expression is like this: some constant a, which is normalization constant, into h n theta. This is a symbol for polynomials, which are called Hermite polynomials. Okay, we will look at the form now. E raised to minus theta square by 2, an exponential factor. This is the structure of where n is equal to, as you know, 0, 1, 2, etc. This is the structure of the wave functions of harmonic oscillator. Okay, and normalization constant a into hn theta, which is Hermite polynomial, and an exponential term e raised to minus theta square by 2. Okay, so first let us look at these Hermite polynomials. Hermite polynomials. These are polynomials in theta. So let me just list the first few polynomials. So remember, the value of n varies from 0, 1, 2, etc. So first value is n equal to 0. So h0 theta, this is the first polynomial. It's 1. Then n equal to 1, h1 theta. It is 2 theta. h2 theta is 4 theta square minus 2, h3 theta, 8 theta cube minus 12, sorry, 12 theta, h4 theta, 16 theta raised to 4 minus 48 theta square plus 12, and so on. So we have written, we have listed first 5 polynomials. So when n equal to 0, it is a 0th order polynomial, that is it is independent of theta. Okay, when n is equal to 1, it contains theta raised to 1. It's first order in theta. N is equal to 2, second order in theta. N is equal to 3, third order in theta. Like that. Not only third order. Another thing we have to, so it depends upon this n decides the order of this polynomial. It's an nth order polynomial depending upon the quantum number n. So we can see that the wave functions are quantized. Okay, these are the energy eigenfunctions, and these are the quantized wave functions in terms of the Hermite polynomials. So n decides the order of the polynomial. And one more point is that for even 0 and even values of n, for example n equal to 0, right, it's independent of theta. N is equal to 2, the expression for Hermite polynomial contains only even power of theta square. N is equal to 4, here it contains theta raised to 4 and theta square. So for 0 and even values of n, this polynomial contains only either independent of theta in case of h0 theta, or it contains only even powers of theta in the case of h2 theta, h4 theta, h6 theta, etc. That in other words, it's an even function in the case of even values of n, 0 and even values of n. And for odd values of n, see h1 theta, it contains only theta. h3 theta, it contains theta cube and theta. So for odd values of n, this polynomial contains only odd powers of theta. So it's an odd function. So this Hermite polynomial is an even function for 0 and even values of theta. It's an odd function for odd values of theta. Okay. So that's all about, we will plot these functions a little while later. Let us look at this normalization constant. So this is normalization constant. Now this normalization constant can be evaluated using the normalization condition of the wave function. What is the normalization condition of the wave function? That is integral minus infinity to plus infinity psi n theta mod psi n theta square d theta equal to 1. This is the normalization condition on the wave function. Now when you apply this normalization condition, then when you substitute for psi n theta square, you have to substitute from here in this expression. Okay, so naturally you have to use the normalization condition for Hermite polynomials. Okay, now when you use normalization condition for Hermite polynomials, I am not going to use, you do the complete calculation here. You can evaluate A. Okay, the expression for A will look like this. Square root of beta, this quantity is inverse characteristic length. Beta inverse is the characteristic length. Okay, inside the root pi raised to half 2 raised to n factorial. Square root of beta by pi raised to half 2 raised to n factorial. That is the normalization constant. So if we write the wave function now, okay, in using the complete normalization constant, etc., the wave function will look like this. Psi n, instead of theta, let me now write beta x. Theta is beta times x. So let me write wave function in terms of x. Square root of beta by pi raised to half 2 raised to n factorial hn, instead of theta again let me write beta x, e raised to minus theta square by 2. What is theta square? Beta square x square by 2 for n is equal to 0, 1, 2, etc. These are the energy eigenfunctions. You can see that the eigenfunctions are quantized. Energy eigenfunction is in the sense that these are the eigenfunctions of Hamiltonian operator. Okay, remember that again, time independent Schrodinger equation is an eigenvalue equation of Hamiltonian operator. So the energy solutions are energy eigenvalues. The solutions are energy eigenvalues of Hamiltonian operator and eigenfunctions of Hamiltonian operator. Or short form we call them energy eigenvalues and energy eigenfunctions. Okay. So this is the plot of the first 4 eigenfunctions of harmonic oscillator. Okay, linear harmonic oscillator. So this is left hand side gives the wave function, and so let us say this is psi 0, psi 1, psi 2, psi 3, etc. and the right hand side gives the corresponding probability densities. Okay, for n equal to 0, psi 0 square, psi 1 square, psi 2 square, psi 3 square, etc. We can see both the positive and negative halves in negative amplitudes in the wave functions, whereas there are only positive amplitudes, so square of the amplitudes in the probability densities. Okay. Now we will see the other details soon. Let us look at the properties of these wave functions. Okay, so properties of wave functions psi n x. The first property, let us look at the ground state wave function. Okay, let us see the expression for the ground state wave function. So this is the general expression. Okay, psi n beta x is some constant, normalization constant, okay, into hn beta x, which is the Hermite polynomial, e raised to minus beta square x square by 2. Okay, so what is the ground state wave function? Put n equal to 0. You see the n starts from 0. So we can say psi 0x. Okay. Now when you put n equal to 0 in this normalization constant, 2 raised to 0 is 1 and 0 factorial is 1. Then square root of beta by pi raised to half. Okay. What is this beta? Root of, what was the expression for beta that we have used? Yeah, consider this. Beta equals root of m omega by h cross. Now beta is inside the square root here, so it will be m omega by h cross all raised to 1 by 4, and pi raised to half is also inside the square root, so it is pi raised to 1 by 4. So what you get is m omega by pi h cross raised to 1 by 4. Okay, so I will write it here. Psi 0x, the ground state wave function. The normalization constant is m omega by pi h cross raised to 1 by 4. And then what is the Hermite polynomial h0 beta x? H0 theta is nothing but beta x is 1. So the 0th order Hermite polynomial is 1. Then e raised to minus beta square x square by 2, and again beta square is m omega by h cross. Okay, so beta is square root of m omega by h cross, so beta square is m omega by h cross. So we have Hermite polynomial is 1, so we have the exponential term e raised to minus m omega x square by 2 h cross. M omega by h cross comes from beta square and then x square by 2. So this is the this is the ground state wave function. Okay. Now if you look at this, let us look at this. This is nothing but a Gaussian function. Okay, when you have this is some constant, m omega by pi h cross is a constant, or all raised to 1 by 4 is the normalization constant. Then what you have is e raised to minus, again m omega by 2 h cross is a constant, so e raised to minus some constant, some, let us say some a x square. So e raised to minus x square is called a Gaussian function. Okay, a bell shaped, if you plot it you get a bell shaped curve peaked at the mean position. Here the mean position is 0, x equal to 0. So this is peaked at x equal to 0. On either side it is a bell shaped decrease. Okay, but it's a bell shaped curve. So ground state wave function is a Gaussian function. Look at the plot here. See in this plot, look at psi 0x. This is the plot of the Gaussian function. It is peaked at the mean position x equal to 0. Okay, and this bell shaped curve. This is the ground state wave function. Okay. And naturally the square also will be a Gaussian function, but because when you square it, this normalization constant will become m omega by pi h cos raised to 1 by 2, and e raised to minus, you get this 2 will go when you square it. So e raised to minus m omega x square by h cross. So the square of the wave function probability density is also a Gaussian function. So this is an important property. Ground state wave function is a Gaussian function. A Gaussian function. Okay, and you try to remember the expression for this ground state wave function. Okay, it's very characteristic property of this harmonic oscillator, linear harmonic oscillator. Okay, m omega by pi h cross raised to 1 by 4, that's the normalization constant. E raised to minus m omega x square by 2h cross. M is the mass of the oscillating particle, harmonic oscillator, right? Omega is the angular frequency. Okay. Now let us look at the parity of the wave functions. Okay, it is noted here in this expression. You can see that for n equal to 0, look at the wave function. N equal to 0 wave function has even parity. It is symmetric about x equal to 0. Okay, here it has odd parity. For example, if you place a mirror and look at n equal to 0 wave function, if you place a mirror here, the wave function on the left hand side and wave function on the right hand side are exactly equal. And but when so it has, this is called even parity. Okay, symmetric about x equal to 0. Here the symmetry is opposite to each other. For example, if you place a mirror, the wave function part on the left side is negative of the wave function on the right hand. We can say psi of minus x is negative of psi of x. So this has odd parity. This has even parity. N equal to 2 state has even parity. N equal to 3 state has odd parity, etc. Okay, so we can say that this n equal to 0, 2, 4, etc. states have even parity. That is represented by plus. Okay, that symbol in the figure. And n equal to 1, 3, 5, etc. states have odd parity. Okay. This specific parity, so we can see that each eigenstate has a specific parity. This is so in the case of, if you remember, this is so in the case of the eigenstates of a particle in an infinite potential well also. Okay. Now the specific parity of each eigenstate is a consequence of the symmetry of the potential function about the origin. Here the origin is the mean position of the harmonic oscillator. So each eigenstate has a specific parity because the potential function here is symmetric about the origin. For example, this 1 second. Look at the you can also see the plot of the potential function in the figure. In the two figures, the potential function is also plotted. We can see that v of minus x is equal to v of x. What is the expression for the potential energy function? Half kx square, right? So it's clear when x goes to minus x, potential energy function is the same. So potential energy function is symmetric about this origin. Origin is the mean position, x equal to 0. Okay, it's symmetric. You look at the plot of this outline gives the plot of the potential energy function. It's parabolic. It's symmetric about the origin. Not simply parabolic, it is symmetric about the origin. That's the important thing. So when the potential function is symmetric about the origin, its consequence is that each eigenstate has either even parity or odd parity. Again, remember the case of particle in an infinite potential well. There also the potential function is symmetric about the midpoint of the box. We have taken the box from the width of the box from x equal to 0 to x equal to L. then about x equal to L by 2 the potential function is symmetric. That's why the wave functions have a definite parity about the mean position, about the mean position there. That means about the x equal to L by 2 point. It's not about the origin, not about x equal to 0 in the case of particle and infinite potential well. Okay, so what the symmetry of the potential function is reflected in the symmetry of the wave function. Symmetry of the wave functions is a consequence of the symmetry of the potential function. Okay. Then okay, then other properties we can, again, you remember how we discussed it in the case of particle and infinite potential well. For odd parity states, okay, that is n equal to 1, 3, 5, etc. There is a node at the mean position. Look at the figure. You have two odd parity states here, n equal to 1 state, n equal to 3 state. Okay, you have a node at the mean position or at the origin. Origin is the mean position. So whatever be the point about which the wave function is showing a definite parity, here it is x equal to 0 point. That point, that mean position will be having a node. A node means a zero displacement point. Okay, antinode means a maximum displacement point. So this is true for any odd parity state, not simply a property of harmonic oscillator. In infinite potential well also we have seen this. So we have node at x equal to 0. There is mean position. And what about even parity states? Even parity state, we have an antinode. Okay, or there is a maximum value. So even parity states, let's say maximum value at x equal to 0. Look at n equal to 0 state here. Okay, there is a maximum value. Look at n equal to 2 state, there is a maximum value in the opposite direction. Okay, we can say there is an antinode. Okay, this is true for any odd parity state and any even parity state. Okay, and the next property we can say for the nth state. Okay, for the nth state, the number of nodes is n and the number of maxima or antinode is n plus 1. Number of node is n. For the 0th state, no node. For the first state, 1 node. Second state, 2 nodes. Third state, 3 nodes. Or nth state. Okay, n number of nodes is n and number of maxima is n plus 1. 0th state 1 maxima, first state 2 maxima, second state 3 maxima, 4 maxima for third state, like that. Number of maxima is n plus 1. Okay, let me write it here. Okay, I can continue below. So the fourth property is that for the nth state, number of nodes is n, number of maxima or antinodes is n plus 1. Okay. Now, next important point is about the way the wave function behaves beyond the classically allowed regions. So what is the classically allowed region for a harmonic oscillator? Now, classically allowed region is, for example, you consider this n equal to 0 state. Okay, consider the plot of the potential energy function here. Okay, now the total energy is this much. So when at this point, what happens at these two endpoints? These are called turning points. See, now at this point, the potential energy function, the plot of the potential energy function, okay, you look at this n equal to 0 plot. So at this point, at this particular point, the plot of the potential energy function, that is this parabola, it crosses with, or it intersects with the total energy plot. This line represents the total energy. Total energy is a constant. What is the value? Half h cross omega for n equal to 0 state. It's a constant. So it reaches here. So it means that at this point, what about x less than this point? At x less than this point, total energy is greater than potential energy. At x equal to this point, okay, whatever be that point, here total energy is equal to potential energy. What happens when x is greater than this point? Consider this point here. Okay, at this point, that means my idea is that at this point, let's say, okay, this x value corresponding to this intersection is this here. Now consider a point slightly beyond this here. What is the potential energy for n equal to 0 state at this point? What is the potential energy? Okay, in order to find that, you draw a line from here to the potential energy function. It is somewhere here. This is the potential energy value along the y-axis. This is the potential energy value corresponding to this position. What is the total energy value? Total energy value is again here, half h cross omega. Its value is here. So at this point, potential energy value is greater than this total energy value. So if potential energy is greater than total energy, we know that total energy is equal to kinetic energy plus potential energy. So at a point, if potential energy is greater than total energy, it means that the kinetic energy has to be negative. Okay, so this point and all these points beyond this, all these points are classically forbidden region. If you consider a classical harmonic oscillator like a simple pendulum or a loaded spring, okay, oscillating, then this point is the maximum up to which it can go. It represents an amplitude. It's also called a turning point. See, consider the oscillation of a simple pendulum. It goes to the right side. Let's say it's go to the right side, and at one particular point, its kinetic energy reduces to 0. Okay, when kinetic energy reduces to 0, what is its total energy? Equal to potential energy. Correct. That is called a turning point. Why it's called a turning point? Because at this point, the pendulum stops, the bob stops, and it turns back to the equilibrium position. Okay, and it goes to the other extreme, to the left side. To the left extreme, again its kinetic energy reduces to 0. At that point, total energy is equal to potential energy. And there also it stops and it turns back. These are called turning points. Okay, that's for a simple pendulum, for a loaded spring. So at this turning points, okay, this is one turning point, and on the left side also you can see that turning point. At this point, potential energy is equal to total energy. So potential energy equal to total energy, or total energy equal to potential energy. These are the classical turning points. And beyond that, when x is greater than these turning points, and within the classical turning points, total energy is always greater than the potential energy value. This is true for any state. Consider n equal to 1 state. These are the turning points. Within the turning point, when x is less than the turning points, total energy is greater than this potential energy value here. But beyond the turning points, when you have a point here, okay, potential energy value is high, whereas total energy value remains here. Potential energy is greater than total energy, which means that kinetic energy is negative. This is not allowed. So these are called classically forbidden regions, when position is greater than turning points. So for a classical oscillator, it cannot go beyond the classical turning points. It cannot go beyond the turning points. What about the quantum oscillator? We have plotted the wave functions here. You can see that, for example, for psi equal to 0 state, the plot is like this. The wave function extends beyond the classical turning points. For each state, you can see that this is the classical turning point, but psi 1 has a value beyond that. It exponentially decreases beyond that, and but still it extends to some region beyond classical turning points for all the wave functions. So naturally, probability density also extends beyond the classical turning points. Okay, see that. It means that there is some very small probability of finding the particle in the regions beyond the classical turning points. Okay, where total energy is less than potential energy function. Now we have seen that this type of a situation in finite potential well. There also the plot of the wave function and hence probability density extends beyond classical, the classically forbidden regions, extends beyond the boundaries of the potential. So if we consider a particle with energy less than the height of the potential barrier, beyond the boundaries of the potential, the energy, total energy will be less than the potential, the height of the potential barrier. Okay, total energy will be less than the potential barrier. That's a forbidden region and classically forbidden region. Here also, so we can consider harmonic oscillator potential half kx square as a finite potential. This can be considered as a finite potential well. A particle is oscillating within a finite potential well, and it can extend beyond the classical turning points. That's the idea. So this is an example of quantum tunneling. Okay, the fact that the quantum oscillator can it has a finite probability of getting detected beyond the classical turning points is an example of quantum tunneling. So that is the next property we can write here. So psi nx in for each value of n extends beyond the classical turning points. Okay, so the particle has a very small probability of a finite probability of getting detected or getting found beyond the classical turning points. So this is an example of quantum tunneling. Okay. Now let us compare in the next property. Let us compare classical probability and quantum probability. I mean the probability of a classical harmonic oscillator and a quantum harmonic quantum oscillator. Okay. For example, so let us compare the probability of a classical oscillator and a quantum oscillator. So let us see what is the probability of a classical oscillator. Okay, let's calculate that. Consider a classical oscillator like this, for example a simple pendulum. Okay, this is the mean position. It oscillates like this. So let me consider 2 points here. Let us say x and another point here x plus dx. Okay, they are nearby points. Okay, so let us calculate the probability that the particle is found between x and x plus dx. So what is the probability that the particle is found between x and x plus dx? How do we calculate this probability? Okay, let us make this argument. It's a ratio of the time it spends, the particle, okay, or the oscillator, the time it spends between x and x plus dx, okay, divided by total time taken for one oscillation. Let's see if this is true. Total time taken for one oscillation. See, consider this figure. Um, Out of the, let's say the total time taken for one oscillation is 1 second. Okay. Then out of 1 second, a few milliseconds it spends between x and x plus dx. So out of the total time of 1 second, how many milliseconds it spends between x and x plus dx? Out of total time, how much time? So out of a total amount, how much is this? That gives the probability, right? So the probability that the particle is found between x and x plus dx is the ratio of the time it spends between x and x plus dx, and out of total time taken for one oscillation, what's the fraction of time it spends between x and x plus dx? That's the idea. Okay, so let us evaluate this quantity. So let me use a symbol like this, px dx. Okay, probability of detecting the particle between x and x plus dx. Okay, so how do we calculate the time it spends between x and dx? So what is the time for crossing the distance dx? It is distance by velocity. Let's say script v represents velocity. So the time it takes for the particle to cross from x to x plus dx is distance by velocity. Let us say the velocity is v, distance by velocity. But it crosses from x to x plus dx twice during one oscillation. Okay, suppose it is going to the right, then it crosses once, then it comes back from the turning point, then it crosses again. So during one oscillation, this particle crosses from x to x plus dx and then back from x plus dx to x. So 2 times it goes. So the total time it spends between x and x plus dx is 2 times dx by v. Okay, and divided by capital T, the time period of the oscillation. Okay, so now we want to find out what is the velocity of the oscillator. This you have done in your higher secondary classes. Okay, consider an oscillator like this. So its displacement at the time t you can write as a sine function or a cos function. Let us use this a sine omega t, where a is the amplitude of oscillation, the displacement corresponding to the classical turning point. So what is this v? Velocity at the position x. Okay, velocity at the position x. So v you can find out as dx by dt. Okay, what is this? Sine omega t, derivative is cos omega t with an omega coming outside. So a omega cos omega t. Okay, so that's equal to a omega cos omega t. You can write as 1 square root of 1 minus sine square omega t, right? So that's equal to a omega square root of 1 minus. Now again sine square omega t, look at this first expression, x equal to a sine omega t. So sine omega t you can write as x by a. So I am trying to write the velocity as a function of x. Okay, so sine omega t you can write as x by a. So for sine square omega t becomes x square by a square. Take the LCM inside the square root. So you have root of a square minus x square divided by a square. Take the denominator a square outside. So you have 1 by a outside, and this 1 by a cancels with the a outside. So velocity at the point x, velocity varies with x, is omega times root of a square minus x square. This is the expression for the velocity of a classical oscillator. Let us see whether this is correct expression. What happens at extreme points? Extreme point means turning points at x equal to maximum amplitude a. At x equal to a, you have root of a square minus a square, that is 0. Velocity is 0. This is correct. At the extreme point, the pendulum, the bob stops and it turns back. And where is the velocity maximum? At x equal to 0, at the mean position. At the mean position, velocity is maximum. It quickly passes through the mean position, and the value is omega into a when you put x equal to 0. And at the extreme positions, velocity is 0. So this expression is correct. So let us substitute this value in our expression for the probability. Okay, so the probability is 2 times dx divided by omega into root of a square minus x square whole divided by, and t time period you can express in terms of omega, it is 2 pi by omega. Okay, Therefore, the expression for the probability of finding the particle between x and x plus dx is 2 will cancel, omega will cancel, so you have dx by sorry, not omega, dx by pi into root of a square minus x square. Or we can say that the probability, roughly you can get this idea, the probability is inversely proportional to velocity, you can say. If you look at the first expression, probability is inversely proportional to velocity. So why we say that probability is inversely proportional to velocity? At near the extreme points where the velocity is small, the particle spends more time at the extreme points because the velocity is small. So there is more chances of finding the particle near the extreme points. Near the mean position, the velocity is maximum, so particle quickly passes through the mean position. So the it spends very small time in around the mean position, so the probability of getting detected is small. For example, if you take look at an oscillating pendulum, and if you take snapshots of this pendulum continuously for some, let us say 10 minutes, then if you look at these photos, snapshots, in most of the snapshots you will see that the particle is near the extreme positions. Okay, in very few photos you will see the particle near the mean position. That's it. So the probability of getting detected near the extreme positions is large, and the probability of getting detected near the mean position is small. So we can say probability is inversely proportional to velocity. So this is an exact expression, probabilities dx by pi into root of a square minus x square. Let us try to plot this. Okay, and we will compare with the maybe, yeah, let us try to plot it here. This plot expression. So if we plot it, I will plot it near the side. Okay, so if we plot this value, this is mean position. Okay, let us say these two are the classical turning points, minus a and plus a. These are our amplitudes, right? Okay, let me just mark the classical turning points here. So a classical oscillator cannot go beyond this classical turning points. If you look at this expression, see at x equal to 0, when the probability at x equal to extreme positions, what is the probability? Put x equal to a, plus or minus a. So a square minus a square is 0. Okay, 1 by 0 is infinity. So at the extreme positions, probability is infinitely large, and the probability is a minimum at mean position, because at mean position x equal to 0. So denominator is maximum in this expression. That means probability is minimum at the mean position. So the mean position probability is somewhere, let us say some minimum value. At the extreme positions it is maximum. So if we plot this graph, it looks like this. It looks like something like this. So this is the probability of a classical oscillator. Let us compare with that of a quantum oscillator. Okay, we have already plotted here the probability densities. Look at n equal to 0 state. The probability density is maximum at the mean position, and it goes to small minimum at the extreme position. So it goes to very small values at the extreme positions, and it extends beyond the classical turning points. But see the contrast, it is maximum at the mean position, and it decreases towards the extreme positions. It's exactly opposite to the probability density of a classical oscillator that we have plotted here. Okay. Okay, look at this. It's exactly opposite to this. For classical oscillator, at all, it's maximum at the extreme positions and minimum at the mean position. And for psi 0 square, for quantum oscillator, for n equal to 0 state, the plot is exactly opposite. Maximum at the mean position, and decreases towards the extreme positions. And for another point that we want to note is, for classical oscillator, this probability is independent of energy. For all energies, all vibrational energies, probability is the same. Our argument is the same for all energies for deriving this probability. But for quantum oscillator, we can see that for n equal to 0 state, probability is like this. For n equal to 1 state, it's different. It's a minimum at the mean position, but it's maximum at 2 different points. And it varies for different energy. So its energy, it varies with energy. Okay, probability of a quantum oscillator is different from that of a classical oscillator, and also it changes with energy. Okay, but let us see what happens when n becomes very large. Now I have copied from the net a plot here showing the comparison of classical probability and quantum probability. Look at n equal to 0 state. This violet curve represents classical probability, as you have seen here, and this reddish curve represents quantum probability. Okay, it is, its area is also shown here. So there is a very large contrast between classical probability and quantum probability. Classical probability is inversely proportional to velocity. And for n equal to 2 state, this is the situation. For n equal to 1 state, this is the situation. N equal to 2 state, this is it. N is equal to 3 state. So you can see that these first 3 plots, first 4 plots we have already seen. So there is a contrast. So classical probability and quantum probability are different. Okay, but as n increases, let us see what happens. For n equal to 10, this is the situation. Okay, this is the situation for n equal to 10. There are n nodes and n plus 1 maxima, and you see that the amplitudes of these, even though there is a fluctuation, what is the overall behavior? You can see that the amplitudes towards the mean position are smaller, and while the amplitudes of the probability density, okay, towards the amplitudes of the probability density plot towards the extreme positions are larger. So the overall behavior of this quantum oscillator, the probability density of the quantum oscillator, approaches that of the classical oscillator. Okay, so as n increases, the probability of a quantum oscillator approaches that of a classical oscillator, and this is also an example of, another example of Bohr's correspondence principle. We have seen that we have discussed about this correspondence principle while we were discussing Bohr atom model, I think. So here also this is another illustration of the correspondence principle. Okay, even though it generally the quantum the probability of the quantum oscillator differs from that of the classical oscillator, as n increases, the probability of the quantum oscillator approaches that of the classical oscillator, because the large n region is classical domain. As n becomes large and large, the system becomes more and more classical. Okay, that is the reason. So these are the different properties of the energy eigenfunctions. Okay, we have seen the plots of the first 4 eigenfunctions and probability densities, and this is a comparison between the probability of a quantum oscillator and that of a classical oscillator. Okay, now we can stop the discussion. Now we will look at a few problems on linear harmonic oscillator in the next class. That's all.